Let's move on to part 4. You can use interfaces for callbacks. Some limitations of the measurable interface is you can add measurable interfaces only to classes under your control, and measuring an object in only one way. Callback is a mechanism for specifying code that is executed at a later time. The responsibility of measuring lies with the added objects themselves. Alternatively, give the average method both the data to be averaged and a method of measuring. So you create an interface, measurer, and it takes an object. All objects can be converted to objects, so you can send anything this way. The code that makes the call to the callback receives an object of the class that implements this interface. So average would basically receive an object of measurer. The average method simply makes a callback to the measure method whenever it needs to measure any object. So here we've got measure, and we call an object on it. A specific callback is attained by implementing the measurer interface on an object. So we don't care about the type, but we must cast from object to rectangle before we call it. To compute the average area of rectangles, you construct an object of area measurer class and pass it to the average method. The average method will ask the area measure object to measure the rectangles. The data class, which holds the average method, is decoupled from the class whose object it processes. You provide a small helper class, area measurer, to process rectangles. This detaches and decouples the classes involved here, so you can use them again and again. So, interface measurer computes the measurement of an object, and it has a single method. Area measure implements that measurer, and it actually can call through and get the right details. And then when we actually use it, we call the appropriate object as a callback. So let's talk briefly about lambda expressions. Using a method such as average is a lot of work. You have to define your own method, etc., sometimes even your own class. That's why you don't find many such methods in the standard library. Java makes this easier using what's called a lambda expression. A lambda expression works with interfaces that have a single abstract method. Such interfaces are called functional interfaces because interfaces are similar to mathematical functions. Lambda expression specifies parameters, the code for computing the return value, but that's about it. The example of a lambda expression is a function that gets the balance of a bank account. Takes an object as a parameter and then calls the getBalance on the method. Lambda comes from a mathematical notation that uses lambda instead of the symbol arrow. In Java, a lambda expression cannot stand alone. It must be assigned to a variable whose type is a functional interface. Now the following actions occur. A class is defined that implements the functional interface. The single abstract method is defined by the lambda expression. An object that the class is constructed. The variable is assigned a reference to that object. You can also pass a lambda to a method. So, for example, here we're going to pass in the lambda as a method of average balance instead of having to define a separate method and then pass it in. Another way to deal with trivial classes is declare them inside a method. So you could have a static method, main, with a class inside it only visible to that class. It's like a box inside a box. You can declare inner classes inside an enclosing class, but outside its methods, it's available to all methods of the enclosing class. So here's another example class. The compiler turns an inner class into a regular one with a really weird name. It's called mangled. Inner classes are commonly used for utility classes that shouldn't be visible to anybody else. Why would you use an inner class instead of a regular class? It's convenient for small, tiny classes. Also, their methods can access local and instance variables from the surrounding scope. When would you place an inner class inside a class but outside any methods? When the inner class is needed by one or more methods. So this brings us to mock objects. If you want to test a class before the entire program is completed, you can build what's called a mock object. A mocked object provides the same services as another object, but in a simplified manner. If you just want to practice arranging the Christmas decorations, you don't need a real tree. Similarly, when you develop a computer program, you can use mock objects to test parts of your program. So example is a gradebook, grading program which manages quiz scores. Using class gradebook with methods add score, get average, and save. If you want to test grading program without having a fully functional gradebook class, you can declare an interface with the same methods. Conventionally use the letter I as a prefix for the interface name, I gradebook. both the mock class and the actual class implement the same interface, so in theory you can just exchange them. The grading program only talks to interfaces, not the implementation, and that way you can swap them out. Meanwhile, provide a simple mock implementation restricted to the case of the one student and without saving functionality. Very simple, very easy to use for testing. Now construct an instance of mock gradebook and use it immediately to test the grading program. When you are ready to test the actual class, simply use a gradebook. Don't erase the mock class. It can come in handy when you need to do testing later on. Why is it necessary that the real class and the mock class implement the same interface type? You want to implement the grading program class in terms of that interface so that it doesn't have to change when you switch between the mock class and the actual class. Why is the technique of mock object particularly effective when gradebook and grading program are developed by two programmers? Because the developer of the grading program doesn't have to wait for the gradebook to be complete.